I wanted to talk through problem 2 from the written assignment, which was a commonly missed question. So in problem 2 on this written assignment, you were given two different subsets of P2. So now P2 is the collection of all polynomials degree 2 or lower. And then with A and B, you're given an additional criteria so that we're dealing with a subset of that collection of polynomials, P2. Now, P2 is known to be a vector space. It's one of our standard vector spaces. It meets all 10 of those axioms that are required of a vector space. And so the question is going to be whether this subset that meets this additional criteria, so in the case of A, we're talking about the polynomials degree 2 or lower, such that the derivative of the polynomial at 2 is equal to 0. We want to determine whether this subset of P2 itself constitutes a vector space, and so then that would be a subspace of P2. So there's a theorem that says when we know we're dealing with a subset of a vector space, instead of having to prove all 10 axioms or to show that it meets those requirements for a vector space, we really just have to prove 3 of them, and then the other 7 will come automatically. And those criteria are that the subset contains the 0 vector for that vector space, and that the subset is closed under addition and scalar multiplication. This says contains right here. I know I'm still working with this really crummy tablet it's not real sensitive with my handwriting. But yeah, that says contains. Okay, so the 0 vector, it's specific to a vector space. 0 vector can mean different things depending on the space. For example, I mean, if we're working in R2, like the set of xy pairs, then the 0 vector is the vector 0, 0. Or if you're working in R3, the 0 vector is the vector 0, 0, 0. In a collection of functions like this, the 0 vector is just the constant function f of x equals 0, which I'll write here. Oh boy, okay. The constant function f of x equals 0 is what I'm trying to write there. That's the 0 vector for this vector space. So then the question is, okay, so does it meet this criteria? So first of all, yeah, a constant function, it will always be in P2. It doesn't matter what the constant here is. If it's f of x equals 500, that's a degree 0 polynomial, so it's degree 2 or lower. It meets that requirement. The derivative is the derivative at 2, 0. Well, the derivative of any constant function at any value of x is always 0. So yeah, I mean, then f prime at 2. See this? So the tablet it's sensitive here, so my writing looks fine. I'm just defending myself. It's not my handwriting, or it's not all due to my handwriting. It's partly due to this tablet. All right. Anyway, so sure, the derivative of that constant function f of x equals 0, evaluated at 2, would be 0. So yeah, it contains the 0 vector. Is it closed under addition? So to determine whether it's closed under addition, let's say we take any polynomial, or polynomials, I should say plural, P and Q from this subset W. So that means that the derivative of P at 2 is equal to 0, and the derivative of Q at 2 is equal to 0. And then let me slide this over. So then the question is, does P plus Q belong in W? Which the question there is, if we take the derivative of the P plus Q function and evaluate it at 2, do we get 0? Because that would mean that yes, P plus 2 belongs in W. Well, it's one of our properties of derivatives that says, sure, the derivative of the function P plus Q is just the derivative of P at 2 in this case, plus the derivative of Q, whoa boy, again at 2 in this case. And since P belongs in W, P prime of 2 at P prime of 2 is 0. And since Q belongs in W, Q prime at 2 is 0. And so P plus Q prime at 2 would be 0. So yes, it's closed under addition. Lastly, if we take a scalar C multiplied by a function P that belongs in W, does that belong in W? So again, the question there is the derivative at 2 0? Well, when you do a scalar times a polynomial, or times any function actually, you can just pull the scalar out and then take the regular derivative of P at 2. That's always the way we take derivatives. You just leave the scalar out front, you leave that alone, and then multiply by the derivative of the function over here. Since P belongs in W, then P prime of 2 is 0, and so you've got a scalar C whatever it is times 0, so this is going to equal 0, which means, yeah, okay, C times P also belongs in W. So yes, this subset is closed under addition and scalar multiplication. So in part A, this is a vector space. Or, well, I mean, what I said is true. It's a vector space, but specifically it's a subspace. Oh, yikes. All right, this is supposed to say subspace. It's a subspace of P2. I'll give that one more shot. Subspace. Yikes. Okay. You know what I mean. Now, B, you're given different criteria. So forget the P prime of 2 equals 0. This time we're saying that the derivative at 2 needs to be 1. This subset actually fails all 3 of these requirements. But since this video is already 7 minutes long, I'll go with just the first one. Does it contain the 0 vector? Well, again, I mean, the 0 vector for any collection of functions is just the constant function f of x equals 0. And the derivative of that function at 2 is going to be 0, not 1. So this set right here does not contain the 0 vector. Ooh, that's supposed to say contain. This is supposed to be an I. So it's not a subspace. But also, just to drive home the point, closed under addition, if we do P plus Q, take the derivative at 2, you're going to have 1 plus 1 equals 2. It's not going to equal 1 anymore when you do P plus Q. So it's not closed under addition. And if you do a scalar C times P, the derivative at 2 is going to be C times 1, which is C, which is, I mean, sure, in one specific case when C equals 1, that would work, but in any other case, it's not going to belong in W. So it doesn't contain the 0 vector. It's also not closed under addition or scalar multiplication for part B here. So part A, turns out with this criteria, yeah, the 3 requirements are satisfied. But when you changed it from P prime of 2 equals 0 to P prime of 2 equals 1, now it doesn't contain the 0 vector. It's not closed under addition, and it's not closed under scalar multiplication. So in part B, this is not a subspace.